Today has been a very long day. I don't know if I'm streaming or if I'm not streaming, but I believe I am streaming to everybody out there in Tube Land. I still have my tie on from another presentation that I was just involved with. So good afternoon. It is Q&A Friday. And thank you for tuning in for a little Q&A. All right. Before I get started, I wanted to remind you, if you're connected with me on LinkedIn, there is a session you are not going to want to miss. And I am going to put a link. I'm going to put the LinkedIn link in the chat box over here. I'm also going to put the Facebook link in the chat box. And this is going out on YouTube, Facebook, and Twitter. For those of you watching on LinkedIn, I'm going to do that separately since and I don't know what TW is. TW, is that Twitter? I think it's Twitter. I'm going to put that one in. This is an event that you're going to want. This is Ask the Expert session on harmonics. And the individual who's doing this is Dan Carnevale. And I believe he's going to be live at the Experience Center. And what's really going to be unique about this event is he will be presenting and showing and demonstrating harmonic issues and the resolution. And if you know Dan Carnevale, smart individual, he's probably forgotten more about harmonics than I ever remembered or knew. And he is going to help us understand harmonics, what they are, and their impact. We'll be able to visualize it. I'm telling you, you are not going to want to miss it, and it's free. Nihad, are you going to be in there? You better be there, Nihad. Didn't think that you were going live today when you were not live at noon. I know, and here's what the problem was. I was on a task group meeting, correlating committee task group meeting. What was it on? It was healthcare. So we were going over the load calculations for healthcare. I believe that was the one at noon. Yeah. So I had that task group went quite long. I thought it was going to be a quick one. And then I had a medium voltage task group right before that because we're creating a new Article 235. So I changed my time and I did not get to go this morning. It's just been today has been a rough day for a Friday. So anyway, the other thing I am going to do on LinkedIn, because I really want to stress, you do not want to miss this event with Dan Carnevale on harmonics. And I'm going to put it, link to that in the chat box on LinkedIn as well. So Steve roaming in the house. So I'll tell you, Steve, we were going over, there's a desire to change the demand factors in healthcare for receptacle loads. You know how we did the changes on lighting for lighting loads, and that was driven by ASHRAE standards, et cetera. But the receptacle, so what's happening in the healthcare industry, and I know this is not necessarily related to Q&A Friday, but what's going on in the healthcare industry is they do their load calculations, and you know how we do our load calculations for receptacle loads, VA, so many VA per receptacle. And if you think about a operating room, there's requirements that are not driven by the National Electrical Code. They're not driven by NFPA 99. They're driven by other codes that basically require a large amount of receptacles inside, say, certain areas within a hospital, like an operating room, which I've never seen the inside of. I don't want to see the inside of an operating room. I don't, even on a tour, I do not want to see the inside of an operating room. So in any case, there's a large number of receptacles inside of an operating room, and then that influences the load calculations. And so what we're trying to do in this task group between panel 2 members and panel 15 members, hopefully I got those numbers right, is come up with some language. And we have some healthcare engineers involved. Krista Bison, who's on panel 13, I think. Jason D'Antonis, who is the chair of panel 99, and a few others. Very smart individuals who do healthcare for a living, and that's what they do on a daily basis. So we're trying to come up with consensus. And that was a really good meeting. And it went a little longer. And then I had a meeting with Chuck Mello and with Keith Laughlin, and we are going to, this is for the next Tuesday, IAEI News Live at noon. We're going to have a discussion on grounding and bonding, and it's going to be, you are not going to want to miss that one either. So you're going to want to, there's just so many cool things going on, Nihad. It's just, and I got some really good news. Oh, it's 3:00. So I got some really good news on the marina front as well. I'm not going to share anything yet, but because I don't want to jinx myself, but I've got some activity going on that hopefully will translate into great things for safety for the marina environment. So if that comes to fruition, I'll let you know. And if it doesn't, I'll let you know I failed. But working hard for electrical safety. That's what we do. That's what Nihad El Sharif does. That's what Steve Froming does. And many other people who help and watch this program. So thank you for all of you do for electrical safety. It makes a difference. It really does. We're saving lives. Okay, so this is what? Q&A Friday. And why am I not talking about Q&A? So I'm going to just pull up some language here. Are you ready for Q&A Friday? How does an arc energy reduction maintenance switch affect downstream series rated breakers? From JW. Well, how does an arc energy reduction maintenance switch affect downstream series rated breakers? How does it affect it? Well, first off, let's start with
unknown.
I love these unknown caller things. And you know what that is? My auto insurance is expired. You know what? I had another one. You're gonna love this one, Nihad. I'm driving back from Michigan while I'm calling up a PowerPoint presentation, so I'm just giving you some ad lib here. But I had a phone call as I was driving down the road, minding my own business, and I get a phone call, and I just, you can just tell her to answer, and she answers. So I said, "Hello, this is Thomas," and they said, "Do you have debt?" And I said, "Do I have debt? Whoa, do I have debt? I've got debt." And I said, "Can you help me with my debt?" And she's like, "I think we can. What is the credit card?" I'm like, "Oh, it doesn't have to do with a credit card." I said, "I know I owe a lot of people phone calls. I got to get back, so I need help." And I kept her on the line for quite some time, but I don't think she was trying to call me to help me with my debt. I think she wanted to get some specific numbers so that she can build upon that debt. But any case, that was an interesting discussion. So the arc reduction maintenance switch, think about what it is and what it does. An arc reduction maintenance switch is something you turn on when you have to perform justified energized work downstream. So if you think about, I'm looking for a one-line diagram. I've got so many PowerPoints, you would think, here we go. Let's do this one. So, whoops. Oh boy. So that's an arc flash event. Oh my goodness, nothing works when you want it to work. Okay, here we go. That's what I wanted to hit. All right, so let's take a look at this behind us. So remember when I work on equipment, and let's say I'm going to do justified energized work in this panel, the incident energy that I'm exposed to is dependent upon the clearing time of the upstream overcurrent device over there. And that could be a molded case circuit breaker. It can be a power circuit breaker. And remember that, and I've got programs on this. I can say, for example, an 800 amp breaker. I can buy an 800 amp molded case circuit breaker, an 800 amp insulated case circuit breaker, and an 800 amp power circuit breaker. All three 800 amp devices, but very different in the amount of energy that they'll let through, because that power circuit breaker can hold those contacts closed for up to 30 cycles. Think about that. Up to 30 cycles. One cycle is enough to give you a heat and pressure to just do some damage. But 30 cycles can really turn into a lot of incident energy. And if I'm doing justified energized work here, and I use that term, justified energized work, because that's an important thing to understand. When it's justified, I take that panel cover off and I'm going to, I don't know, say I'm troubleshooting. Good example of justified energized work. And I need to take voltage measurements. I'm going to need to dress for the energy. And that energy in this panel is not based upon the main overcurrent device in that panel. It's based upon the overcurrent device feeding the panel. So let's say, for example, it's a 30 cycle delay. Circuit breaker upstream, I can equip that circuit breaker with an arc reduction maintenance switch that such that when I turn it on, it doesn't have a 30 cycle delay. It trips in less than a cycle, or maybe 2 cycles, or faster than 1 cycle. I can reduce the amount of energy at this panel when I'm in there doing my measurements. What does that translate into? That translates into lower personal protective equipment ratings. So maybe I'm not into a 40 cal outfit. I'm into, I don't know, 4 calories of an outfit. I'm not wearing a balaclava. I'm wearing gloves, because I can, when I reduce the incident energy, I'm not only reducing the incident energy, but I'm reducing my arc flash boundary. Why is that important? If I've got, like, say 28 calories and my arc flash boundary is in feet, my entire body is in the arc flash boundary. My entire body needs to have personal protective equipment. If I can reduce the incident energy and reduce the arc flash boundary, my arc flash boundary could be inches. And now my head is not in the arc flash boundary. I may not even have to have a balaclava. I might be able to get away with a lighter and lower rated personal protective equipment. And why is that important from a safety perspective? Is it just because, hey, it takes me time to dress up? No. When I'm in a 40 cal outfit trying to operate probes, it can be clumsier. It can be more difficult. If I can reduce the severity for the electrical worker, then I can put the worker into a more flexible dress so that it's easier and less likely for them to make a mistake, drop something because of the gloves or whatnot. And then we'd have a whole different debate on whether or not the gloves or the dexterity, all that other good stuff. But in any case, I can get you into a lighter dress. Now, let's go back to the question that was asked by JW. He says, how does an arc energy reduction maintenance switch affect downstream series rated breakers? Oh, you can tell I'm tired. Okay. If you think about when you have a series rated system, and we just talked about this last, maybe Tuesday? I don't know. I think it was Tuesday. We talked about short circuit current ratings and series ratings, the motor contribution. It was Tuesday. So if you have a series rated system and your available fault current is going to be high enough that it's basically in the instantaneous region of your upstream and your downstream device, what does that mean? Why do I know that? Because my bolted fault current value is so high that my upstream and my downstream device are both going to clear the fault. If, depending upon where my arcing current is, now remember, the time current characteristic curve, when I talk about incident energy reduction due to an upstream overcurrent device, I'm not talking about comparing the bolted fault current with the clearing time. Hey, Robert, good to see you too, brother. I'm not talking about the bolted fault current clearing time with the upstream overcurrent device. I'm talking about the arcing current. And the arcing current is going to be a lower value of current. What do we use to calculate arcing current? What document, what reference is IEEE 1584? As long as I'm within as long as I'm within the parameters, what do they call that? The limitations of IEEE 1584 with regard to voltage, with regard to available bolted fault current, grounded versus ungrounded, all these great different. You'd have to take a look at 1584 and look at the scope and all that good stuff. As long as I'm within those limits, then I calculate two values of arcing current, a lower and a higher, and then I use both of the clearing times of that based upon my overcurrent device. I don't compare my three-phase bolted fault current value when I'm calculating incident energy. So I can have a very high, if my bolted fault current value is so high that I'm worried about the interrupting rating of the downstream device, because in a series rated system, the downstream device has 10,000 amp interrupting rating and the upstream device will have a 65,000 amp interrupting rating. Together, they can interrupt up to 65,000 amps. If I am not worried about the 10K doing its job, it's because the 65K device upstream is probably going to be opening those contacts and clearing that fault with the downstream device. So I'm in the instantaneous region for the three-phase bolted fault current value of both overcurrent devices. But remember, the incident energy of the downstream equipment is based upon the clearing time of the upstream equipment. And for example, if I'm in this piece of equipment and I am series rating the main overcurrent device with a branch device in this equipment, that has nothing to do with the arc flash energy determination in this equipment. Because why? Because my incident energy is not based upon the main device in this equipment. It's based upon the feeder upstream in that other bigger gray box that is feeding this panel. The clearing time of that device at the lowest and highest arcing current to determine the incident energy here. Now, if I am series rating a device external and internal, so say I'm doing a series rating of the feeder breaker to this device inside of this equipment, and that's what I'm using for my series rating, the chances of your arcing current being in the instantaneous region of the upstream device is probably high, which would mean I don't necessarily need an arc reduction maintenance switch. In fact, 24087 is written such that, and let me tell you a little hint. The article 240 and 250 are very similar when you're not wearing your glasses. So if you are looking at 250.87, you're going to have a little bit more difficult of the time talking about what I'm talking about, so it's put your glasses on and look at 240.87. It says that one of the means shall be provided for 1200 amps and above. An instantaneous trip setting and temporary adjustment of the instantaneous trip setting to achieve arc energy reduction shall not be permitted. So if you're instantaneous, if your arcing currents are high enough, then you don't need to have any technology on that 1200 amp and or above piece of equipment. You see what I'm saying? So JW, there's no real easy answer to your question, but I can say it has nothing to do with the series ratings. The arc reduction maintenance switch doesn't have anything, it doesn't have any effect on a downstream series rated breaker. None whatsoever. It's a different goal, different task. But the relationship would be all around, where is your arcing current with regard to instantaneous? If it's already in the instantaneous region, then you don't need one of these other technologies. Technically, by the code. Right? So technically, per the code, you don't need it, but there might be other reasons why you want it. Because an arc reduction maintenance switch can look down further into the power distribution system. So hopefully that answers your question. In the graphics you show where motor fault current contribution affects adjacent circuit breakers fault current, I don't see how 240.86C, 240.86C. Motor contribution. So 240.86C, I'm just going to go to, we're talking interrupting ratings, right? So that's basics, and I go to interrupting ratings, and we'll just call that slide up just to see. I know which part you're talking about, which I don't have. Series ratings. I opened the wrong PowerPoint. Okay. Let me look at my motor contribution, and let's take a look at that one. Worth taking a look at. All right, so what we've got here is failure to communicate. So JW says, in the graphics you have shown, where motor fault current contribution affects adjacent circuit breakers fault current, I don't see how 240.86C is written properly to address this concern. Instead, it seems to be written to address only a series rated pair at a given motor, or a motor's connected in the middle of a series rated pair. That would be correct. I would agree with that, JW. Remember, I've got two devices. I've got this main device up here, and I've got that device down there. This, not the one that's right here in front of my finger, on the other side, down, that's upstream of the fault. So that device and the device that's above where that fault is are the two devices that I need to series rate. The motors that are here, these motors, contribute the fault current that is in between those two devices. That's what we're talking about. And if, for example, I don't know if I can do this. I don't see why I can't do what I want to do here. So if, for example, I'm going to go back So if my fault is here, so if my fault is there, I have utility contribution going to the fault. I have this motor contributing to the fault and that motor contributing to the fault. So I have those two motors contributing fault current, which if these two exceed 1% of the interrupting rating of this device, then, which if it's 10K, 100 amps, if these two motors exceed 100 amps, not this one, I don't have to worry about that one because it's downstream. If these two motors exceed the interrupting rating of this device, 1% of that device. And what does that mean? That means that this motor and this motor are in between these two devices. That's a problem. So what your question was, your question said, I'm just going to, in the graphics you have shown where motor fault current contribution affects adjacent circuit breakers fault current, I don't see how 240 is written properly to address. Instead, it seems to be written to address only the series rated pair at a given motor or motors connected in the middle of a series rated pair. And that's the way it's supposed to be written. So your interpretation of it is actually accurate. And hopefully I conveyed that. You're worried about two devices in series, two breakers in series, or a fuse upstream of a breaker and motor contribution in between because the downstream circuit breaker is going to see more current than how we test it as a series. Max Yield, I like your name, Max Yield. Thanks, Thomas, for sharing your vast amount of knowledge. I appreciate it, and I appreciate you because this is how we learn. JW out there, Robert from Omaha, and Nihad El Sharif and others all contributing. Is there a way us viewers can help support you? Always a way. And where there's a will, there's a way. Do things right. Pay attention to the details. That's how you can support me. I don't know how to do the financial stuff. I don't know. I'm not doing it for financial gain. I just want to share information. So I don't like these things. I'm going to remove this one. Some of these people put comments in that are like links to places you don't want to go. Okay, so since the new, but thank you, Max Yield, for the kind words. Thank you very much. I really appreciate it. Means a lot. You just helped me, brother. You pumped me up. Since the new rule 24087 may apply when someone is replacing a breaker in a switchboard. Ooh. What happens when someone is installing a downstream breaker over 1200 amps and that breaker was originally configured to be series rated, and now you have to have a fast overcurrent setting for arc energy reduction? It would present a greater hazard to install such a thing, and forcing one to replace the entire switchboard instead of just one breaker is a lot. Let me read that again. Since the new rule 24087 may apply when someone is replacing a breaker in a switchboard. I get it. So you're taking a breaker out of a switchboard, you're going to be replacing it. What happens when someone is installing a downstream breaker over 1200 amps? So I guess you're replacing this downstream breaker with a breaker that's 1200 amps and above. And it was originally configured to be series rated. And now you have to have a fast overcurrent setting for arc energy reduction. I would say, JW, I think you're overthinking it, in my opinion. Because remember, if you're doing a series rated application and it's the downstream breaker, you have an interrupting issue anyway. And if it's 1200 amp breaker, and you have an interrupting issue because your available fault current is higher than instantaneous, where do you think the arcing current's going to be? In the instantaneous region. If it is, then 24087 says you can just use instantaneous. You don't need an arc reduction technology in that application. So I'm not getting where you're going. I'm not buying what you're selling. I'm not catching what you're throwing. And I could just be missing the entire point. That is not new for me. So in any case, JW, I think you just need to take a look at what the requirement says. And remember, instantaneous is an effective means to meet this requirement. So that's all I'm saying about that. Good morning, Robert from Omaha 3 days ago. 3 days late and saying good morning, but better late than never. What a great way to promote the industry by taking us on a walk through NFPA. And this was Power Systems Engineering and Applications, introducing us to the wonders and amazing things that affect us and the trade industry. You are welcome. Sharing your content to the Electrical Code Ninja group on Facebook. Thanks. Excellent, Mr. Snyder. Please share and share alike. Be more than happy. And remember, and that was based upon the Breaking IAEI News Live. So, again, IAEI News Live, get out there to that, to the IAEI's YouTube site. There's a lot of great information out there. Ryan commented, on Tuesday when I was supposed to be going live at 5, I was on the phone with Mike Holt. Mike called me. I believe it was 5 o'clock. Mike called me and we got into a discussion. We were talking about resistances, and I realized I was late for my live session, my Tech Tuesday, and on series ratings. And I said, hey, I said, Mike, oh my gosh, I'm supposed to be going live. He goes, well, let's go. And I'm like, all right, let's go. So we continued our discussion live. And Ryan's commenting that he used to drive Mike insane when he would want to talk about series ratings on his videos, and he had no interest at that time. And he says, what a funny coincidence. Hey, Ryan, good to see you, buddy. That was an interesting coincidence, wasn't it? But I always say when guys like him and you and others call me with a question, it's not going to be an easy one, but it was an interesting coincidence. I didn't realize that that he was giving you a hard time. Times change, brother. Times change. William Snyder. Hi, Thomas. How does the motor contribute to the fault if there is no motor on the faulted circuit? Also, on the one-line diagram you showed at 55 minutes, why is the fault current on the generator bus so much higher than the utility? Oh, I know what I'll do. I know which one you're talking about. This is the series ratings discussion. And he wants to know, and I'm going to see if I can find it, which I might not be able to find it. I hate when here's what I do. I decide to go live, and I don't save my PowerPoints. I just go live. So I am going to open up my series rating. No, this was not series ratings. Oh my goodness. Well, I'm just looking. I know where that one-line diagram is, and I'm not going to try to call the video up, but I'm looking for that single-line diagram. But so here's the thing. Before I try to find that, let's just talk in general. I made a mistake one time. I was doing a presentation on selective coordination to a group of healthcare type of people and engineers. And I made a mistake one time, and I said that the available fault current will always be greater from the utility than from the generator. And I had a hand go up in the back of the room. And I said, yeah, but how can I help you? He says, I disagree with you. I said, with what? And he says, I disagree with you when you say that the utility available fault current will always be greater than from the backup generation. He goes, I do some hospitals where the generator available fault current from the combined generators exceed the available fault current from the utility. And I said, I wasn't talking about healthcare. So, and I'm sure it's not just healthcare. So I'm not sure where that's at. But I think I would say, in general, it's not a safe assumption to say the available fault current from the generator will always be less than from the utility. So that specific one-line diagram, because I do remember making a change in my PowerPoint slide decks, and I know that that diagram is out there somewhere, because you know how we all do this. We copy and paste presentation materials. I am sure that that's probably from my little learning experience in that presentation. And that is my little nugget of joy for all of you. Be mindful that the available fault current could be larger from the generator. Jeffrey Romani, however you want to say it. As a newbie on learning about transformers, this was on the comment for the 15-minute tech talk I did on the 75 kVA transformer. I'm telling you, if you want to look at the sizing of the overcurrent protected devices, sizing of the feeder and secondary transformer conductors, take a look at my 15-minute tech talk on the 75 kVA transformer. I did a few of them. But Jeffrey says, as a newbie on learning about transformers, I was a little confused about the formula I used. After rereading my text and doing the calculation according to the text, I got approximate values for primary and secondary current full load amps. Happily, I realized that your formula is a shortcut and accurate within an approximation. I will use it in the future for swift calculations. Thanks. Good video for newbies like me. And I'll tell you what he might be talking about, primary and secondary. So here's my thought process. So remember, on these transformers, if you're doing your full load amp calculation, if you calculate the secondary, you can get the primary simply by reflecting the secondary to primary based upon the turns ratio. So I can take my secondary full load amps, multiply it by the secondary line-to-line voltage divided by the primary line-to-line voltage, and that'll give me my primary full load amps. And to his point, within an approximation, because remember, if you think about, I don't know how many decimal points some people carry things out to, but I'll never forget, I had somebody give me a available fault current. You know, I asked what the available fault current was, and to the class, and they do the math, and one of the engineers raised his hands up and says, "I got it." And I said, "What is it?" He goes, 43,362 amps, 0.57764. And I'm like, you had me at the first two digits. The accuracy on how many decimal points you take things out to matter in some cases and don't in others. The full load amp calculation, if you think about accuracy in doing calculations, and I remember I have a book called Numerical Analysis, and I talked about it in one of my other programs. I think it was last week. I went through a power systems engineering library, and my numerical analysis class, we talked about error margins. And if you think about error when you're doing calculations, you've got a couple things you got to think about. One, if you're using an HP calculation like this versus an Excel spreadsheet versus maybe another calculator that I don't know, doesn't have the same accuracy as this. You have the simple accuracy of the tool, which would be how many decimal points you're taking out your answers to. And in addition to that, when you start with calculations, like for example, full load amps of a transformer, you're going to take the kVA divided by 3. It's going to be a whole number. It's going to be a nice even number. There's not going to be any decimal points. But in that same equation, you have divided by kVA. And if you take the 3-phase kVA, divide that by the square root of 3, now you have an equation, and within which there's another equation. You have what we would call a series of accuracy within. You have the accuracy of a calculation within the accuracy of another calculation. The decimal points matter. So if I take, for example, if I take 4160 and the square root of 3 is 1.7321, if I take the 4160 and I divide that by 1.7 and I don't put the 1.7321, then I'm introducing an error, and that's only one. That's a calculation within another calculation. So when you add these things up, it all matters. So what I did in this example was I calculated the secondary full load amps of, let's take a, just for giggles, let's take a 1500 kVA transformer, a 1500 kVA transformer, 4160 to 480 volts, and let's calculate the secondary full load amps. Let's do this, because we love to do this. All right, so here is what we are going to do. I am going to change my background, and hopefully we can make this happen. All right, so I have a 1500 kVA. How you like them apples? $1,500 kVA transformer, 4160 to 480 volts. Let's calculate the full load amps, right? So this is how we roll. We're going to do an equation. I don't want that there. So 4160 to 480, I want to do insert an equation. And we're going to do it here. And we're going to say, remember, full load amps is kVA. Oh, man, I tell you. Should have just stuck with a white background. I don't know why I did that. And let's increase the size. And here's what we're going to do. We are going to do this. We are going to go to equation. We're going to do that. Get rid of that. And we're going to say this is kVA. Is that how you do it? You do kVA. kVA times kVA times what? Square root of 3. You're going to go, what is he talking about? kVA times the square root of 3 divided by 3 times kV. How do I get that? How do I get that? Because technically, down here, in this little spot here, I should have put this in. kV, divide that by the square root of 3, right? Square root of 3. And then I don't need to put this in. So I've got a couple different equations that I can use. This is the long way. I have kVA divided by 3 because if it's a 3-phase transformer, I've got to divide my kVA to get it to a single phase kVA. And then I divide that by kV, which if it's a 3-phase kV, I have to divide that by square root of 3. So if I take that square root of 3, which is in the denominator, and put it in the numerator, now I am into this equation up here, right? So that's the basic equation. And this is what I'm talking about when I say the fact that, you know, it's that little math that I do here, which this is going to give me a decimal. And if I round that and I include that, then it just rounds things out. So now let's do the math. That equals 1500, right? That is equal to equation. Do that. That is equal to 1500 divided by 3 times. And that is going to be on the secondary, it's 480. I'll do a 0.48 because there's another piece of math that I'm just doing the assumption of. And I'm going to divide that by the square root of 3. All right, so let's, what does that turn out to be? So I got 1500, divide that by 3 is 500, divide that by 0.48. And I'm going to multiply that by square root of 3. 1804.2196, 1804.2196, but we don't typically say it's 1804.2196. We say the full load amps is 1804. Now, what is the full load amps on the primary? Let's do it the long way. So we're going to take this for primary. I'm going to delete that. For the primary full load amps, Control C, Control V. It's 1500, but I got to change the voltage to 4.16, right? 4.16. So if I do it the long way, I take 1500, divide that by 3, divide that by 4.16, and divide that or multiply that by square root of 3 is 208.1792. 208.1792. And now, if you think about the other thing that I can do, I'm going to insert another equation. I'm just going to do that and make this white text. And I'm going to increase the size of this. So what I can do is take secondary full load amps. I second that equation. I secondary times V secondary, divide that by V primary, and that equals I primary. So let's do it. I secondary is 208. I'll do the 0.1792 to keep everybody happy. And I'm going to say times new duplicate. I am going to I'm going to make this smaller. I'm going to put this over here. And I'm going to make this smaller. And I'm going to put this over here. And I'm going to put this up here where we can all see it. So 208 times V primary divided by V secondary, or or V secondary divided by V primary. And I'm going to do this. 480 divided by 4160 equals, drum roll please, 208.1792 times 480 divided by 4160. Did I get the right numbers? Nope, I used the wrong number. 1804. Whoa, it's I secondary. 1804.2196. Just seen that. 1804.2196 times 480 divided by 4160 is 208.1792. 208.1792. So if you carry all the decimal points out, now if I just did 1804 times 480 divided by 4160, I get 208.1538, which is a little different than 208.1792. I would still say 208 amps. So you can just simply do that math, and that's what he was talking about. All right. Hello from Ryan Jackson's channel. What is that, Ryan? It says, I love CO Mountains. And it says, hello from Ryan Jackson's channel, and it's got the smiley face. I don't know what that is, brother. But anyway. Okay. Now, I've exhausted the questions on YouTube. And now I'm going to go back to my emails a little bit, because I did get some emails with some questions. And there's a link breaker question from Roger Zieg. By definition, if there was an, oh, yes. I believe that Article 230 does not have an overcurrent protected device reference because it is a service. By definition, if there was an overcurrent protected device, the conductors would become feeders. Roger, you are right smack on. And let me tell you what he's talking about. Oh, man, we were... doggone it, I can't remember the PowerPoint and what the topic, oh, goodness gracious. I remember it, but I can't remember it. In any case, remember we were talking about the feeder rules, about the demand. It was Q&A from Friday. So that was July 27th. Great job in breaking down the solution in a clear manner. And it was, I believe that 230 does not have an overcurrent protected device reference because it's a service. By definition, if there was an overcurrent protected device, the conductors would become feeders. It is for this reason I'm allowed to run feeders through a building to another building, but I cannot run a service in the same manner. Roger, you are absolutely correct. And I'm trying to remember the specific section. Oh, man. And it was, it's right on the tip of my nose. But in any case, that is correct that when you have a service overcurrent protective device, the moment you land conductors on the secondary, it also is a feeder overcurrent protective device. And I think in the discussions that we were having, we were talking about a branch circuit and a feeder, and that there weren't similar rules in 230 for service overcurrent devices. And it was, and I can remember talking to John McCamish about this, and the reason was not for what we stated in that video. It was because the moment you land a conductor on the secondary of that breaker, it could be it's a service overcurrent protected device, but it's also a protecting the feeder. So you have to follow the rules of the feeder protection, which puts you into 215. And obviously it's a service over current protected device, which puts you into 230. So I think that this discussion is a good example that an overcurrent device can serve two functions and have to meet two different areas of the National Electrical Code. So be mindful of that. So that was a very good observation, and I wish I had the entire context for you. But I'm looking for another question that I had. If I can't find another one, and I know I had a few, and I just keep forwarding them. Here it is, questions. Okay, this was a good one. Surge event. A surge event damaged an existing installation, meter center. Do I have to replace the entire thing, or can I refurbish it? Ooh. So this is an actual question, and I had a phone call with this gentleman, a great electrical inspector who's trying to help the contractor out and know what, can he approve something or not? So in this case, they had a meter center that damaged one of the compartments, and I didn't have pictures of it, but he said it's very extensive, the damage to that cubicle. So it's like you can't just say, hey, I'm going to brush it off and be back up and running. They'd have to reconstruct one of those, one portion of the meter center. And so he said, how do I address this? What do I use as a reference to say whether I can or cannot fix this up? So a meter center, if I look at the listing of a meter center, now he wasn't on the latest version of the code, which looks at whether you can and cannot recondition or refurbish it. So what I went to was there is a reference for there's a reference from Nema on water damaged equipment, but also Nema fire damage, I think it is. Yeah. So this was the reference that I sent him to. Evaluating fire and heat damaged electrical equipment. Because what his point was that this cubicle, you can physically see that this equipment got a lot of heat. And so what I did was I said, look, take a look at this evaluating fire and heat damaged electrical equipment. It's a free download. And once you download it, it talks about, and it says fire and heat damage. So it doesn't necessarily mean that the equipment was in a fire, but it speaks to all the different types of equipment: enclosed switches, busway, panel boards, transfer switch, switchboards, etc., on whether or not you should replace the equipment or you can recondition it. So this is a great reference to answer his specific question. Use this reference to point to and read through it. It's a free download off of the Nema website. But now if you get into like a 408, is it 408? I'm throwing numbers around like they're going out of style. 408 is switchboard, switchgear, and panel boards. If you think about what is a, I got to find his email to get the exact language. Oh, doodar, a meter center. So think about a meter center. That meter sockets, meter centers. I believe they are listed to the same. Is it? It's not. It's a meter center. Is it UL 414? trying to find the, no, it's not a UL 414. Boy, I tell you, you'd have to look at the standard from a perspective of what is a meter center listed to. You got meter stacks, and I'm just looking for the actual, I'm looking for something other than Tom telling you. Well, what about Pearl standards? Yeah, we talked about that too, Robert. There are other documents, but if when you're dealing with a piece of equipment that is manufactured, so if you go to Pearl, Pearl doesn't make the product, but if you go to Nema, National Electrical Manufacturers Association, and they tell you what to do based upon what then that's a consensus type of document. So you have all the manufacturers. It's not like one manufacturer over another. They're telling you, and in that document, they give you the information that, look, sometimes you can repair, sometimes you need to replace. Yeah. So the socket is a 414. Yeah. Okay. So a meter center, and this is, I just wanted to confirm this, a meter center is listed to UL 67, which is panel boards for a panel. And if you look at 408, and I'm going to look in the 2020 version of the code, but I believe there's a requirement in 408 that says thou shalt not. It says, okay, 408.8, reconditioned equipment, reconditioning of equipment within the scope of this article shall be limited as described in 408.8A and B. And B and A says panel boards shall not be permitted to be reconditioned. This shall not prevent the replacement of a panel board within an enclosure in the event the replacement has not been listed for the specific enclosure, blah, 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 blah. So I would fall back on the fact that it's listed to a UL 67 specification for panels. I would say that it wouldn't be a jump or a huge leap to put you into 408.8. But if you're not on the 2020 version of the National Electrical Code, then you would, watching with the code ninjas, William Snyder in the house, then I would say you would fall back to the manufacturer's information, which I would quote that Nema document, which is on Fire Desert for this specific application, which is a surge-related event, which has burn and heavy heat damage to the equipment. The other area is Nema's policy on reconditioning of equipment. So if you're on an older version of the code, you can go to the Nema policy on reconditioned electrical equipment, and this gives you a background. And I know it was just redone, but in any case, you'll see components or assemblies not suitable for reconditioning, and meters, meter sockets, and if you look at panel boards, they're in here too. Are panel boards in here? Wait, this is not the latest version. Hold on. Let's try this one. Ba-dum. Next. Looking for the document. We just updated this. Nema policy, reconditioned. Let's just do Nema reconditioning. New guide on reconditioned electrical equipment. Let's try this one. This should be it. I'm crossing my fingers. The talk on Tuesday on the one-line diagram you showed at 55. Why is the fault current on the generator bus so much higher than the utility? So we had that discussion earlier, but in any case, I think the point I was trying to drive home there is that your fault current from a generator can be higher than what's coming from the utility. And I made that error once a while ago where I had healthcare engineers in the audience, and I made the statement that your available fault current from the utility will always be greater from the utility than from the generator. And they said, no, that may not be true. So I think I changed that slide because of that presentation and what I learned that day, that the available fault current can be higher from the generator. So it's not always going to be lower than from the lower than the utility. Okay, it depends on how many generators you have, how big they are, and all that jazz. Yeah, no, you're perfectly fine. You're perfectly fine, and thanks for asking the question. It filled the time between when I was trying to get this opened. So it's back there, though, if you want to go listen to that discussion. Nema technical position on reconditioned equipment. This is what I was looking at. So this is another reference to answer this one. You'll see what is reconditioned, and this is in alignment with the National Electrical Code. So I'm just perusing through there. This is a free document. You can get it off of their website. I'm just looking for, there it is, components or assemblies not suitable for reconditioning per the National Electrical Code. You got panel boards, receptacles, low voltage lighting, etc. So I would leverage this in your discussion, and this is a nice document because it gets you to all of the areas where you can and cannot recondition equipment. Okay, there was another question in there. Let me find it. So that answers that question about damaged equipment. And smoke and fire damaged equipment is a challenge. I was once on an inspection with an electrical inspector whose question was, we went to a fire damaged home. And he was very point blank with me. He said, okay, Tom, we walked into the living room. And the paint's peeled off the wall, but there wasn't any fire in there. There was smoke damage. I mean, it was very difficult, I had to have my hand on, I had a rag over my mouth because of the odor of fire and smoke. But we looked at lighting fixtures, and we looked at light switches and receptacles that had visible damage from heat. But do you need to replace it? And there wasn't a good reference out there. So from a Nema perspective, we put together this technical position, not a technical position, but a document on titled Evaluating Fire and Heat Damaged Electrical Equipment to say, when do you need to replace it? When can you refurbish or recondition it? And with smoke brings a lot of challenges because there are a lot of, just like water intrusion, and there is a water damaged equipment document out there on the Nema site. Just do a search for Nema water damaged equipment, and they'll tell you what can and cannot be reconditioned. But these, whether it be water or smoke, they introduce impurities that can affect the performance of the equipment. Some equipment you can address, and some you can't. The other question was, can I use a three-phase panel in a single-phase application? This is a good one. And I had this question, and this one just recently came up. I got a phone call, and it was a design engineer. And he said, look, I have a three-phase panel, but I'm not going to use it for three-phase. I'm going to use it for single-phase. And it's a 600 volt rated panel, and it's 208 volts that I'm using it at, or 240 volts. I can't remember. Hey, Felix Sandoval, the Technical Social Distancing Network in the house. So this gentleman wanted to use a three-phase panel rated 600 volts at a lower voltage and in a single-phase application. And he says, do you think I can do that? What would the inspector say? And so I'm telling you, I could not find anything in the National Electrical Code that says you can't do that. From a voltage perspective, I can't exceed the rated voltage, so I can use a 600 volt panel at 240 volts. I can use a 600 volt rated panel at 120 volts. It doesn't matter. As long as I don't use a 600 volt panel in a 4160 application, right? Or a 240 volt panel at 600 volts or 480 volts. because I can't exceed the voltage, but I can go lower than the voltage. So I couldn't find a problem there. And then there was nothing in 408 that I could find that said that a three-phase panel has to be used at three-phase. And there was nothing in an instructions from the manufacturer that said it's a three-phase panel and it cannot be used in a single phase. If I decided to only use 2 legs in that panel, then I don't see any place. And you guys and gals can help me. Where in the code would it be prohibited? And I can't find any place. And I recall years ago talking to an electrical inspector who was a very good electrical inspector who had an installation where they had a 3-phase panel used in a single-phase application. And he called me with the exact same question, and together we could not find anything in the NEC that would prohibit that installation. I'm not exceeding any ratings. I'm not exceeding the rating of the bus from an ampere value. I'm not exceeding the rating of the bus from a voltage value. I have an unused bus bar, but so what? There's nothing in the code that says you have to use that bus bar. The only place that you'd have to think about is if it's on a 3-phase system. Am I balancing it? You know, am I balanced from A to B, B to C, C to A? If I take off A and B to a single phase application, but I use a 3-phase panel board, but I'm only bringing A and B, say a 208 volt application. So in any case, that's I thought it was an interesting question, and I'm challenging you. Tell me the section in this book that tells me I cannot use a 3-phase panel in a single-phase application. I love you for it, but I don't believe it's there. So yes, I think you can use a 3-phase panel in a single-phase application. You just have an unused bar. That's exactly right. And you know, Felix, I don't know where your head's at, but I do not like unused bars. You should always, you know, when you're walking home, if there's a bar, you got to stop in there. But no, it's just an unused bar. That's all there is. All right. Let me take a look at my emails and see. I'm just going to do a search on question because I usually forward these things to myself and I put question in the, where in the NEC does it say you can use it? Ah, Robert, doesn't have to. Right? I mean, in New York City, we allow single phase. Oh, Matt Rabasi, thanks for joining. We allow single phase 240 volts to be used as a single phase 120 volts single phase when replacing a very old fuse box. Absolutely. And that's a low voltage, but that's single phase on a single phase. Can I take a 3-phase panel, put, say, an industrial application, put a 3-phase panel in and supply single phase to it and power my loads? I don't see it being covered. Now, I can't go, Robert, I can't say, well, the code doesn't say you can, right? I mean, the code doesn't tell you everything you can do. It just tells you basically what you can't do, what violates the National Electrical Code. It tells you what you have to do as a minimum. But I can't find anything that I would say requires you to do that. Now I typed this thing question. Oh, here's one. Okay. I'm doing a medium voltage application. Do I have to size my conductors at 1.25 or can I size them for continuous load? Medium voltage equipment is not 80% rated. It's 100% rated. So you do not need the 1.25 factors. It is continuous. It is fully rated. It's 100% rated. So it's not like your 80% breakers and things like that. So what I would suggest is you could go to the manufacturer of the equipment that you're specifying and get their instructions to prove to the inspector that it is 100% rated. They should have that in their literature, but no, you do not need to use a 1.25 factor for continuous loads when you're doing medium voltage applications. The old fuse box has only one phase, ungrounded conductor. There you go, Mather. All right, I'm looking for more of my questions here. Breaker question. That's the 230. Okay, so I already answered that one. Breaker question, that's the same question. All right, here we go. Now I'm getting it. Install a breaker with overcurrent device and emergency disconnect. I covered the surge event already, and I think I don't know. I thought I had another question in here, but I can't find them in my files. There's my Nema stuff. Question, arc reduction. I have a question related to arc energy reduction performance testing. Okay, by newly added 240.67 and 240.87 Charlie on NEC 2020, do consumable energy reduction devices like fuses or arc quenchers get wasted in the first performance testing? Or are there any means to ensure that the arc energy reduction performance is assembled arc resistant equipment without paying the price twice? Okay. What this one is dealing with 24087. Remember, we just introduced a requirement that when you do an arc reduction maintenance system in 240.87, it has to be performance tested. And 24067 is the same way. It says the arc energy reduction protection system shall be performance tested by primary current injection testing or another approved method when first installed on site. The testing shall be conducted by a qualified person in accordance with the manufacturer's instructions. And it says you need to have a written record. But there's an informational note. Some energy reduction protection systems cannot be tested using a test process of primary current injection testing due to either the protection method being damaged, such as with the use of fuse technology, or because current is not the primary method of arc detection. So what they're talking about is that, for example, a fuse, obviously, if I'm using a fuse to do arc energy reduction, I wouldn't want to, throw my current through there, watch the fuse open, and then go buy another one. Although I'd love for you to do that. But that's not required. If I have an arc quenching technology that looks at light and current is not the primary method, a light source is, I could inject current and have it go off and then have to replace the arc quencher because I've just damaged it because I set current through there and it activated. But I haven't really tested it because I need to do the light, etc. I haven't fully tested all of the capabilities of the device. So that's why we put in follow the manufacturer's instructions. And you'll find that some technologies come with test equipment, like our arc quencher. We have instructions testing the arc quencher. We have testing the Eaton arc quencher. There we go. Look at this. Wow. Obi-Wan Kenobi. Look at this. We have equipment that you use to test the arc quencher. And we are so thorough in this instruction sheet that we tell you what all of the settings do. We tell you, we give you a light source. We give you all of the accessory cables. We show you pictures. We even tell you how to plug in the equipment. So this is, we have images and we will show you how to test the arc quencher. And I'll tell you, Mike King, as part of our engineering services division, will actually be more than willing to come out and teach you how to test this equipment in person or in one of our facilities. So you don't have to damage the equipment. We have provisions in the National Electrical Code to give you guidance on how to get it done without damaging the equipment. But if you want to, test all your fuses and buy another ones, you can do that. Just let me know about demand needs and all this other good stuff. But you do not need to do that. All right. I have a question on the compatibility between the GFCI requirement and the AFCI requirement in the National Electrical Code. In general, when it comes to protecting from both a shock hazard and an arcing fault fire hazard, like in a kitchen, what is the typical circuit configuration that satisfies both 210.8 and 210.12? Are there any listed products combining AFCI and GFCI technologies in the same breaker or receptacle? That's a good question. I mean, hands down, that's a good question. And you know what? Because this is the Technical Social Distancing Network, Felix Sandoval, we've got a darn good answer for you. So what we've got here is a solution for your situation. You have a couple ways to address this. Ouch. We have combined products. We have an AF/GF receptacle, which does both arc fault and ground fault, a dual function device. We also have Eaton AF/GF circuit breakers and breakers brochure. Let's take a look. Woo doggy, look at this. AF/GF circuit breakers, the dual purpose. I lovingly referring to them as dual function, but dual purpose arc fault, ground fault, circuit interrupter addresses the 17 requirements. And look, kitchens and laundry areas, which is exactly what this question hones in on. This device is listed to UL 489, UL 943, UL 1699 for AFCIs. 943 is GFCIs and 489 is thermomagnetic circuit breaker. This thing does it all. So you could put a circuit breaker at the source or I was wondering if we have a oh, look at that. That's a nice kitchen. I don't know about you guys, but that's a beautiful kitchen. I love the floors. Look at that. And there's an island. Do you see any receptacles? Anyway. So you could put a arc fault, ground fault to cover the laundry area and the kitchen. You could put it in a receptacle. You can put it in a breaker. And I'll tell you, we make these blind face receptacle or wiring device type solutions that you can feed that if you want to put it on the refrigerator, for example, and you don't want any other loads and you can't put the breaker in, you can put a receptacle in that's a blank face feeding another receptacle, and it'll give you both arc fault and ground fault protection. Or you can just do an arc fault breaker and a ground fault receptacle. That's an option too. So you can put an arc fault breaker protecting the entire branch circuit and connected cords, and then you put a ground fault circuit interrupter receptacle that serves the loads. That's perfectly viable to do that. You can put AF/GF in the breaker. If you protect that home run circuit and follow the rules in 210.12 and you can provide an OBC AFCI downstream, you can put an AFCI GFCI receptacle. You could put an AFCI breaker and an AF/GF receptacle. you're double dutying the arc fault, but there's no compatibility issues between arc fault and ground fault. There's no compatibility issues between any of these technologies. So they can both reside on the exact same branch circuit. No problems with that. Robert from Omaha, do I have a class on this? I think, Robert, I can put one together. And maybe we do a tech talk on arc fault protection and ground fault protection for the National Electrical Code. So what do you think about them cupcakes? Thumbs up? Thumbs down? On the side? Did they give you an indication on which trip? Oh, Daryl Hill in the house? My brother. Yes, they do. You're like a straight man. So what you'll see on these, you'll see a couple things here. How you been, Daryl? I'm like, you don't even write me anymore. You see these little indicating lights. You got indicating lights there, and you've got an indicating light here. And I'll tell you, Eaton, AFCI status light, status indicator with a compass in the stock. So let's take a look at this. Look at the trip codes. Oh my goodness. Oh my goodness. So AFGF breakers are equipped with a red diagnostic LED that blinks a repeating pattern from 1 to 6 blinks, indicating the cause of trip. This pattern is the trip code. Bada bing, bada boom, bada bang. And look at this. No code recorded. No code. The number of the code. And then you have the description. So if it blinks once, it's a series arc. It's a low arcing current that has been detected within one of the current pathways. Oh my gosh, this is, I don't know about you guys, but I'm getting like, wow. You know, it's just like so awesome. What do you think? It's just powerful. Wow. 2 is a parallel arc. 3 is an overload. 4 is over voltage. Did you know that these things will do over voltage protection? Your fault, my fault, nobody's fault. We're going to protect you. $29.95. Let's pick up the phone. Let's give us a call. The breaker will trip if it experiences voltage of 160 volts RMS or greater. The breaker can be reset and the test button can be pushed to verify that the breaker is working properly, most likely caused by a loose or floating neutral. And I'll tell you why this is so important. I used to be product line manager for these solutions. And I'll tell you, I would get phone calls where this is what they would do. They would say all of my breakers would instantly trip when energized. And I'd say, well, there's a problem with them. So I had a contractor, I don't know how many houses they had, all of their circuit breakers were damaged. We had to replace them. And I'm thinking, what is the issue that we got here? Why? And the way they connected the house, they connected it to where they didn't have the neutral. And in a method, in a process that did not have the neutral connected, and they overvoltage, they not only lost our breakers, they also lost radios and other things that we didn't know about until after the fact. In another case, they would disconnect the main and they would build one of these suicide cords. And they have pills for that. So they took these cords and they took a generator and they would power the house through a receptacle, which would backfeed back through the equipment. So anyway, they were doing things that would cause problems, but we've got over voltage protection. And look at this: ground fault, ground and neutral, and then they have the self test. So yes, Daryl, we got it covered. Got it covered. I mean, when you just look at the capabilities, it's just like, holy crap. I mean, does the value stop? Awesome. Yeah, overvoltage is my fault protection. My fault, your fault, nobody's fault. We're going to shut this circuit down. Robert says, I got to go back. Look at that. We had the old fuse box. We had public image. Do you have classes on this, Daryl Hill? Do they give you an indication? GFCI receptacle work with combo AFCI breakers also. Absolutely. This reminds me of our AFCI paper, Nihad. Right. We got to get that. We got to brush the dust off of it. Very nice. Thanks. Sorry, I gave you a hot flash. They have pills for that. Yes, they do. Awesome. Good questions, though. Man, I got to go back. What time is it? It's 4:30. I'm probably well over my time. So I covered that one. All right. I think that is, hold on, ground fault testing. Nope. All right. Unless I find other little places, and plus it has been fun. It's been real, and it's been real fun. So I think I am going to sign off because I have to make some phone calls. All right, everybody. Thank you for joining in. Thanks for Daryl and Nihad and Robert from Omaha and Robert from Omaha. We got who else? Mr. Abbasi. Thank you. And Felix and everybody else out there. Thank you for what you do for the electrical industry. Thanks for what you do for electrical safety, speaking up on behalf of safety. We need more of that going on. And William, thank you, Mr. Snyder, for joining in. Take care, everybody. I got to sign off. I got to make a couple phone calls. Thanks for everything. And thanks for what you do for electrical industry and safety. And remember, be careful, be well, and stay healthy. I'm not going to be, next week, I am going to be teaching a class. So don't forget to get out there to the IEI's YouTube site. There will be a premiere video going on at 12 o'clock noon next week. Check that out. It's on grounding and bonding. You're not going to want to miss that. The Chuck Mello and Keith Laughlin. Check that one out. So anyway, I believe that's the language in code calls for protection of branch circuit, AFCI, GFCI. Doesn't the branch circuit originate in a panel board? So regular MCCB and GFCI receptacle doesn't quite cover the entire branch circuit. Right. So remember, no, you have a branch circuit requirement to protect the entire branch circuit for AFCIs. GFCIs can be located either in the breaker or in the receptacle. If you put it in the breaker, you're providing AF and GF for the entire circuit. But if you look at the requirements in 210.8a or B, it doesn't mean you have to have it in the breaker and protect the entire branch circuit for GFCIs. So you could have an AFCI breaker in a breaker in the panel board and a GFCI receptacle. That would be permitted per the code. All right, I'm signing off. Thank you. Take care. I will not see you next week. I am going to be teaching a class all week. I will see you on Tuesday on the IAEI website or YouTube channel. Don't forget to go out there. We're talking grounding and bonding with Keith Laughlin and with Chuck Mello. So check that one out on Tuesday. We'll see you there. Otherwise, I'm not going to be going live. I should be able to do a Q&A session on Friday. I believe I'm back in the house. But we will see. Stay tuned for that. All right. Take care. Stay safe. God bless. And please stay healthy.